Today we will in the previous lecture we have looked into how can we design first gain adjustment and then PI, PD and also finally PID. In PID or PIPD, what we want is to obtain the what we call the PID gain. We want to find KP, KI, KD. So we use root locus based on the design specification that was given to the user. We want to design and find KP, KI, KD using root locus. Today, we will discuss another technique to determine KP, KI, KD, determine the PID gain. Okay. So, just to inform you that PID is widely used in industries. Although there are many other controllers, there are many other advanced controllers. You heard about AI, intelligent controller, about fuzzy logic, all those things. But still in industry, the most widely used is PID controller. Why? Because PID is simple, okay, not as complicated as others. And to find the parameter is quite is easier than other controllers. The root locus is one of the techniques we discussed before, but there are many other techniques to what we call to tune PID. When people say tuning PID, meaning to find KP, KI, KD. That's what tuning PID means. Okay, so the tuning generally involves choosing the parameters of KP, KI, KD. So beside root locus, there are many other methods. And today we want to look several methods used to tune PID. And the method can be divided into two. First, closed loop, and second, open loop. So there are two methods, closed loop and also open loop. And the one I in the PowerPoint on the slide are some of the techniques used in closed loop and open loop. And the one that I highlighted in red color are the among the common techniques used in tuning PID. In fact, Ziegler-Nichols is the most widely used, is the most popular technique in tuning PID. So today there are such techniques are Ziegler-Nichols, Tyrus-Lubin, then oscillation methods. That is under closed loop. Under open loop, we have Ziegler-Nichols, Cohen-Kuhn, fatigue, minimum error criteria. So the one which are in red color are the one that we will look into. Ziegler-Nichols and also Cohen-Kuhn. Remember, Cohen-Kuhn only only used in open loop. But Ziegler-Nichols, there are both techniques available in closed loop and also in open loop. Okay, this table summarize what happened if we increase K, increase the value. If we increase KP, KI, KD. If KI increase, KD increase, KP increase, this is what will happen. The rise time, settling time, overshoot, steady state error, and also stability. Okay. But this is just in general. In order to get in detail, we need to analyze each system in detail. In general, this is the one, the effect of increasing K. Okay, now let's move into PID tuning, Ziegler-Nichols. As I said, this is the most popular one. So we will look into Ziegler-Nichols. This method is useful when mathematical model of a plant cannot be easily obtained or not known. That means GS is not known. Okay. Because if we know GS, as what we did before in the class before, we can draw curves and then we can design based on the technique that we have studied. That is if we know model. But if we do not know the system, in some cases we are not able to calculate or model the system. We are not able to get GS. Then in this case, Ziegler-Nichols is good. Okay. This is what we are saying. Ziegler-Nichols first method. First method means open loop. The method use experimental approaches. So in order to implement or to design based on root Ziegler-Nichols, we need to have experimental result. We have to do experiment to tune the PID controllers. And Ziegler-Nichols tuning rule give an educated guess. The one, if in root local we can exactly calculate the value. But in root local, that the value that we will get is just like a guidance. And we need to, after that, to tune a little bit, increase a little bit, reduce a little bit, see what happened. Okay. But that is what we call an educated guess. We can guess based on that value. We can start tuning, proper tuning by using Ziegler-Nichols value. It provides a starting point for fine tune, not a final parameter value. Okay, so we have to understand Ziegler-Nichols or in any other technique also here, like a guideline will help us to start to tune. But final one, we need to do a little more fine tune. Okay, two methods in Ziegler-Nichols, open loop and closed loop. So this is the first technique, first method, which is open loop. See, this is the plant. This is the diagram. See the diagram? Okay. This is an open loop technique where we obtain a system step response by experiment. So we give step response, step input, and we get output. Output is like this. Like output will be in terms of what we call S shape. If we are able to find the output like this, then Ziegler-Nichols first method can be used. Okay, so the shape here, we see the S shape characterized by L. L is what we call delay, time delay. Okay, delay means the system need some time to start to respond. Okay, although input is given earlier, the system take some time to start. Okay, and then it go up. like this, and then settle at K. This is final value. So if we can get S shape, then what we do, we have to do what we call tangent line like this, a tangent, and the one here we obtain here is called L. L is the time delay, and that until here is called T. T is called time constant in this case. Okay. So that is those are the only parameters we need to obtain in order to design or to tune PID using Ziegler-Nichols. We need L and T. Okay. So once we have this is the parameter, the PID gate that we will use. We have to use. Remember, this is PID. And in this case, PID is written by Kp 1 plus 1 over Ti S plus Td. They use Ti and Td instead of Kp, Ki, Kd. But it's the same. If I multiply, open the bracket, last time we have Kp, Ki over S, Kds. They are the same. Kp here and Kp. Ki is equal to Kp over Ti, and Kp equal to Kp multiplied with Td. Okay, if you use this formula, then if the question want Kp, Ki, Kd, then you can convert like this. And all tuning rule use Kp, Ti, and Td, and return in this form. Okay, what I mentioned just now, the only parameter we want is T and L. Okay, L is the time delay, T is the time constant. If we know T and L, we can use this table. See, if I want P controller, P means gain adjustment. My K is T over L. If I want to design PI controller, use this 0.9 T over L for KP. PI L over 0.3. And finally, if I want to design PID, which is normally what we want, so use this value, 1.2 T over L for KP, TI, and TD. If you are asked, if in the exam, all the tuning tables will be given. So you do not have to understand, you do not have to remember the table, but you have to know how to use the table. Right? So that is the first method. Okay, next we will do some example later. This is the second method, Ziegler-Nichols second method based on closed loop. And in fact, this is in Ziegler-Nichols, we normally use the second method. Okay, although first method also can be used. This is in the exam also you see if tuning were asked, we normally ask the second method. Okay, this is also known as ultimate cycle method. We see later why they call ultimate cycle. First, so this is the plan, the closed loop plan, the closed loop system. We have plan. First, we only use KP. Only use KP. Okay, no KI, no KD. It's just K, 1K, gain. It's like gain adjustment. First, set Ti equal to infinity, Td 0, or Ki 0, Kd 0. These are the same. If Ti infinity, then Ki 0. So this is the first step. We need to use Ki 0, Kd 0. So it's like this, only Kp. Using Kp only, increase Kp from 0 to critical value, KCR. This is one of the important parameters. KCR. CR refer to critical. KCR to obtain sustained oscillation. What we do, we will increase K. Increase the value of K until we get this output oscillation. It's like critical value. It's actually when the pole is on the imaginary axis. The system is critically stable, or sometimes we call marginally stable. So we increase K until the system becomes marginally stable, until the system is oscillating, is oscillatory. Okay? Then we have to analyze the result here, the response here, the oscillatory system. Find the critical gain. We want KCR, and the period here. PCR, we call period of the when the critically stable system happen. We need two parameters, two values, KCR and PCR. Then if we know those values, then we can use this table. This is Ziegler-Nichols table. Okay, it's again the same. We can design P, use 0.5 KCR, can design PI, can design PID. Okay, PID, KP 0.6 K critical, TI 0.5 P critical, period, and 0.125 is also period. And multiply with PCR. Okay, so that is the technique for Ziegler-Nichols. If the system transfer function is known, I mentioned just now, these are normally, this is a good technique if we do not know the transfer function. But if we know the transfer function, we can use root locus to determine KCR and omega. Okay, remember, if I have root locus here, let's say 3 poles, it will be locus here and in between, and then it will go like this. Okay. The point here is the critically is critical. Okay, the one that crossing J omega. The system, if it cross the J omega, the pole, if it cross J omega exists, the system become unstable. So this is the point where the system is critically stable. And if we can calculate K here is KCR, K critical. You know, you can use the distance to find K, that is KCR. And the omega here J omega D here is omega n, natural frequency. And can also be given as omega critical. That value we can read from the graph. J is omega CR or omega n, natural frequency. And we know that omega equal to 2 pi f. Right? So f is omega over 2 pi. And we want period. Period is 1 over f is 2 pi over omega. So P critical can be obtained by using this formula. 2 pi over omega critical. Omega critical is the point here. So this is the formula which can be used to calculate P when the system is critically stable. System is oscillatory. Those values are important. KCR and also PCR. K critical and P critical. Okay, let's do one example. Consider the system, the control system in which a PID controller is used to control the system. The PID controller has a transfer function of this. This is PID here, given in this form. A normal form when we use PID tuning. We have KP, 1 over TIS, and TDS. Apply the Ziegler-Nichols tuning rule to determine the PID parameter. We want KP, KD, KI, PID parameters. And here is given the root locus, assuming we know the system root locus. I just zoom at that important point. Okay, here we see this is the important point. This is imaginary axis. The imaginary axis. Then when the closed loop system on the imaginary axis, then the system will be critically stable. That is the point that we interested. Is given here. K is already mentioned here. Is K30. K, if we calculate K, so that is KCR to 30. Okay. If not given, then we know this is 1 minus 5 from the system. Here, that will be like this. Point here is the same here. And we can calculate K by using L1 by L2, L3. Then K, L1, L2, L3 will be 30. is already given in the MATLAB. 30. Also shown here, the frequency, radian per second, is actually here J 2.24. Okay, if you sketch, here also J 2.24. That is already given in MATLAB. So we know KCR, and this is omega critical, which is equal to 2.24 radian per second. And we know, based on the formula, the period is 2 pi over omega critical. 2 pi over 2.2 is actually equal to 2.805 second. Okay, this is period in second. So those are important values, important parameters. KCR, K critical, here K critical, and PCR. Once we obtain those values, we can use this table, these PID tables. Okay, we proceed to calculate those values. Kp is given as 0. For PID, for tuning of PID controllers, a PID controller, we use Kp equal to 0.6 KCR. 0.6, we know KCR 30, so 18. Pi is shown in the table as 0.5 P. 0.5 PCR. 0.5 multiply with, we obtained just now, 2.805. 0.805. 1.403. That is Ti. And Td is given as 0.125. P critical. 0.125, 2.805 is, you calculate 0.35. Those values from the Ziegler-Nichols table. Please remember that. So now we want to proceed to calculate for Ki and Kd. We know that GPID is given as Kp 1 plus 1 over TIS TDS. Kp, our Kp is 18. 1 plus 1 over Pi 1.403s plus TD 0.35 s. We can calculate here like 18 plus 18 over 1.403 s plus 18 0.35 s. And if we equate to remember GPID, this GPIDS is Kp plus Ki over S plus KDS. And then we can equate Kp to 18, Ki, this is Ki, and Kd all here is Kd. So therefore, Kp equal to 18, Ki is 18 over 1.403 is 5.83, and finally Kd 18 0.35 is 0.525. So those are the value of the PID gains, Kp, Ki, Kd. Any question on Ziegler-Nichols technique? So remember what we want to find from Ziegler-Nichols closed loop system is K, the critical gain, and also the critical period. It can be obtained from root locus. Beside root locus, we can also use the Rousseau-Wiss criteria to find the parameter. That means Rousseau-Wiss criteria can also be used to find K critical and also omega critical, then the period, PCR, the critical period. Based on the Rousseau-Wiss table, we can find K, which give system when system is on the critically stable system. When happen row of 0, we can calculate K, then we can proceed to calculate for omega. We do one example, maybe two example later related to Rousseau-Wiss. This is one technique. If we know root locus, then we can also calculate and find K and also P. Any question before we proceed to another technique? The next is tyrus looping. This will not be asked in the exam, just for your information, just for your knowledge. The technique is very similar to Ziegler-Nichols. Also find KCR and PCR. But tyrus looping use a slightly different formula. See, for PI, they use this formula. For PID, they use different formula. That is the only differences. They use different formula. But initially, we have to find the same parameters, KCR, K critical, and also P critical. Okay, let move. Another tuning method is Cohen-Kuhn. Cohen-Kuhn is, remember, only applicable in open loop. When people say Cohen-Kuhn method, mean they use open loop method. It's suitable for use on self-regulating processes based on the characterization of process by a simple first order. And we will show simple first order system. Okay, first order system with a steady state K, time constant tau, and also later date time. Date time also time delay. Normally we use T0. Okay, so in order to do this, a step response. Remember, Ziegler-Nichols open loop also use step response. Cohen-Cohn also use step response. The response is known as the process reaction curve. When we give step response, when we give step input, the output, which is known as step response, is also a process reaction curve. The reaction curve must cover the entire period from the introduction until the system reach the steady state. Okay, so we have to do the experiment. We have to inject input until it start to give response up to the steady state. We mentioned that Cohen-Cohn technique is based on a first order system, and this is the transfer function. Transfer function of a first order system with time delay. Okay. Time delay is T naught. When we have, let's say, normally we have like this, K over S plus 1, for example. But if we have e to power of, let's say, 2s, that means this is a system with time delay of 2. 2 is the time delay, T naught. So this is the one used in Cohen-Cohn. GS transfer function K to power multiply with exponent e to minus T naught S. T naught is the time delay. Divide by, they use tau S instead of S plus something. They use tau S. Tau here is the time constant. Okay, so in Cohen-Cohn, you have to remember those. Remember 3 things. K, time delay T naught, and also time constant tau. And you should be able to write the transfer function. So now this is the response. Input like this is an input, step input. The magnitude of input is delta M. This is magnitude or input magnitude, delta M. And the system, let's say input start from here. See, here the graph here show that the system needs some time to start respond. From here to here is not moving. Nothing happened. The system still did not give any response. So that is what we call delay, time delay. So it start to respond at this point. Okay, so an increase is like a shape, then go to a steady state value. This is steady state. If this is delta C, this is the steady state value. Steady state value. That's delta C. When the system increase during the transient response from, let's say, from the initial point to the steady state value, when it reach 63%, that is called, here is called time constant. Point here to here is time constant. So we need to find the value, which is we multiply 63% with the final value. Then we get we look into the time, and the time from the delay until it reaches 63% is known as the time constant, tau. In Cohen-Coon, we need to find three things. We want K, and this is the formula for K. K is delta C, is the steady state, divided by M. M is the input magnitude. Okay? If input is 1, is input unit step input, then divide by 1. Sometimes the input is not 1, maybe 0.5, maybe 2, maybe 3. It depends on the system. So when not value not 1, we have to divide. We have to divide the steady state value with the input magnitude to get K. We need K. We need tau. Sorry, we need tau, time constant, and also T naught, time delay. So three things. If we manage to find that value, this is the table. Again, we use a table. And the table, if asked in the exam, will be given in the exam. And we just implement those, substitute those values into the formula. For example, for PID controller, Kp is 1.2 over K, T naught over tau, delta 1. Delta 1 means we inverse delta constant tau over T naught. Then Ti, then Td. Any question? We will take a 10-minute break. I will continue with 3 examples. Final exam 2015-16, 18-19. These two are using Ziegler-Nichols. This one also Ziegler-Nichols. And another one, 2014-15, is for Cohen-Coon. So we take a 10-minute break. Then we will continue with doing final exam, past year final exam question. This is the first one is past year final exam 2015-16. Consider a system with a PID controller. Determine the critical gain. So we want to find K critical. And here they want us to find omega oscillation frequency, omega. Omega critical. As in this case, root locus is not given, then we have to use Rosowitz. Okay. If root locus is given, then we can use directly the root locus as in the previous example. If not, then we have to use the Rosowitz. And please, if you forget Rosowitz, please look into it again. Please revise Rosowitz. Rosowitz start by finding closed loop transfer function. Okay, closed loop transfer function. This is GS 1 plus GS is equal to 1 over S plus 1. It's 5, 15. S plus 15. over 1 plus, sorry, we should have KP. Okay, remember when we're doing Ziegler-Nichols, we start with the value of, we start with KP here. The rest are 0. So here should be KP. KP 1 plus
مش يبنر لنا خالص وانا معديها لك
1 plus KP over S plus 1, 5, 15. Resolve, of course, you get this. And if we expand, we get, you can try, I got this one, 21 S squared, 95S plus 75 plus KP. So that is the closed loop transfer function, which we will use in Rousseau-Wills table. We will create a Rousseau-Wills table based on those values. Rousseau-Wills table. Remember, we have S squared, start with the highest order of S, S3, and then become 1 here, 95 here, here 21, and 75 plus KP. 75 plus KP. S1, S0. S1 here, remember, is 21 multiplied with 95 minus 75 plus KP divided by 21. 0 here, and here 75 plus KP. This is the Rousseau-Wills table. Okay, remember, we want to increase KP until we get an oscillatory system, until the pole is on the J omega axis, until there is, the system is a critically stable system. And a critically stable system is happen only if we have rho of 0. Okay. So rho of 0 can happen if here is not already is already 0 if the term here equal to 0. So we get rho of 0 here. Rho of 0 happen when 21 90 multiplied with 95 minus 75 minus KP equal to 0. Then, of course, we can calculate for KP. KP 21 1900 minus 75. 1825. This is KP. In Rousseau-Wills also, we can, once we have KP, we can go one step before, and we can create what we call an auxiliary polynomial. Please revise Rousseau-Wills, in which we can write at 21 here. Here we take here 21 S squared plus 75 plus KP equal to 0. And if we solve this auxiliary polynomial, we will get the frequency on the j omega axis. Okay, so by 21 s squared, by substituting 1825, we get 1900 equal to 0. The s squared is minus 51, which is minus 90.47. Then s is square root minus 4.47. We get complex number j, j 9.81, 9.51. Please also check my calculation. I may get wrong answer. So here is therefore omega n or omega critical is 9.51 radian per second. Once we get omega critical, we can calculate for P. P critical 2 pi over omega critical. Pi over 9.51 equal to calculate to 0.66. We already have Kp. Kp here is also, in this case, Kp here is also K critical. We have K critical, we have P critical. Then we can use the table to get Kp, Ki, and Kd. We can proceed finding Kp from the table. Kp is 0.6 KCR. Remember that formula that is in the table. So 0.6 KCR is 1825. That equal to calculate 1095. Then we have TI 0.5 PCR 0.5 PCR here 0.66. So it will be 0.33. And TD is 0.125 P 125 0.6 equal to 0.0825. These are the values obtained using the formula in the table, and we can write GPID, which is Kp 1 plus 1 over TIS plus TDS. Okay, Kp 1095 1 over 0.33s 0.0825s. So this is the PID controller. Of course, we can equate with the common one. Okay, so KP here is 10. This if we continue here 1095, 1095 over 33s 1095 0.0825s. Okay, so we equate, then 1095 AI is, and KD here is 3318.2 93.34. Any question? Do you have any question regarding this? Okay, let's move. This is another example. Same procedure, same about the same question, but only with different transfer function is here. Okay. Referring to ZN table in Appendix 1, Appendix 1 is in the question. Determine the ultimate gain K. Here they use ultimate. Ultimate is the same. If they use KU, the same as K critical. Okay. It's sometimes people use ultimate, sometimes they use critical. And ultimate frequency, omega. So this is omega critical. That is A. Then again, because we do not have the root locus, we can use Rosowitz. Then the question asks the control tuning parameter using a P controller, only P. When only P, that means you have to use this formula, only this formula. Only one parameter need to be calculated, which is Kp, 0.5 kCr. If they want Pi, if the question asks for Pi, then you need to calculate two parameters using these formulas. When they want PID, then three parameters using the formulas here. Okay, so please be careful what controller is asked. And see here the control tuning parameter using PID. So the question asks for first P, then second PID. This is the same as before. Actually, I have the answer, but I want you to do. It's better you do it. The answer here is KCR, K critical is K 19.2, and then omega is 4.79 radian per second. So that is for A. Once you obtain this, of course, you can calculate for B and also for C. For C, what I got is KP 11.52, PI 0.5655, and PD 1637. Then, of course, from here you can get KP, KI, KD. Using the same method we did before. Please do this as a homework. You can follow the same the procedure that we discussed in the earlier example. Then you should be able to answer this. So you can see that Ziegler-Nichols or tuning of PID is quite simple as compared to calculating PD, calculating for zero in PD controller. Okay. So you should also focus on this because you can see it is quite simple as compared to calculating PD. In the exam, sometimes normally, I'm not sure actually, but we will ask both. The first part, which is calculating PD, and then PD and PID. Also, tuning will also be asked. But normally, tuning give lower marks than the previous one. Okay, please do this because I want to move into the last example. The last example relate to Kuhn-Kuhn. So we did a lot example on Ziegler-Nichols. This is, I think, the only example we have on Kuhn-Kuhn. The system in figure 1 has a first order. This is figure 1. Has a first order characteristic with time delay with transfer function represented here. Remember, we have K is the gain, T naught is the time delay, zeta is the time constant. Time delay, and gain. The output of the time response for the system is given in figure 2. So this is the output. Okay, you see, it's like a shape as S shape. This is called reaction curve. Or this is actually step response. It's in S curve. Determine the value of K. So we want to find the gain, T naught, the delay, and the time constant. This question, I'm not sure this question, but they should also give the input with unit step input. That means the input is what? Okay, now we want to find K. Remember the formula here? K is K is the steady state value C over M, the input. M in our case, I just mentioned unit step response. Unit step. M equal to 1. Okay, so we want to find K. K is the steady state value. Here is the steady state value. Okay, steady state value here 0.9. 0.9 divided by 1. 1 is the input. If input not 1, input let's say 2, then K have to be divided by 2. 0.9 divided by 2. If the input is 0.5 magnitude, then we divide by 0.5. In this case, it's just 1, then 0.9. Okay, next, we want to find time delay, T0, time delay. How can we determine time delay from this S curve? To find the time delay, we need to draw tangent like this. We need to draw tangent similar to this graph. And here will be the time delay. Okay, so we can take, if you can print this one, to improve understanding later, I would suggest you to print this and take a ruler, then make a tangent to the it's quite difficult to do here. Okay, this is a tangent. And here, the one that across the real axis is time delay. In this case is 1. What we get is 1 second. So it will be slightly different among all students. Maybe you get 1.2, some get 0.98. It depends on the tangent that you drew. Right? That is T0. Next, we want to find time constant. Time constant is mentioned as when it happened at 63% of the final value. Final value here is 0.9. If we take 63%, it is 0.567. So we need to take 0.5, here 0.5, 0.6 here, 5, 6, 7. So 1, 2, 4, 6. Maybe here, roughly. This is just an approximate. This is 63%. And if we go down from here to here, from the time delay to this point is called time constant. Perhaps here is 3.1 second. The time constant is 3.1 second. sorry, 3.1 minus 1. Please remember, must be actually 2.1 second. Must be from the time delay to the 60% value. So here 3.1 and it start actually at 1, so 2.1 second. Any question in finding K, T naught, and also time constant?
No, doctor.
No, doctor.
Let's move. If we manage to obtain those values, then it will be easier for us because it is just applying the formula. See the formula here? Kp 1.2 over K. T naught. Kp is 1.2 over K. T naught over T over tau minus 1. It's actually the same. K tau minus T naught. Same. Because they inverse there. 1.2 over 0.9 tau 3.1 over 0.5. Is if you calculate become 2.1, sorry. 0.5, 2 point something, not sure, 2.7, 2.8 maybe. Can someone calculate this one? 2 point something? .7 maybe. Please check this. Okay, then
Doctor.
apa?
The time delay is 1, right?
Time delay, 1, sorry. Thank you. Time delay is 1. Yes. So berapa ni?
2.8.
2.8. Okay, 2.8. Then we have TI. TI is 2 multiplied with T naught. Time delay become 2. TD is 0.5 T naught. 0.5. Therefore, our GPID is KP 2.8 1 plus 1 over 2 S plus 0.5. That is our PID. And of course, you can solve this, you can find KP, KI, KD using the same technique before. Equate to the common formula of PID, then you can get KP, KI, KD. Again, you can see that it is quite easy to get those values and to get to design the PID controller using the tuning rules. We have Ziegler-Nichols and also Cohen-Kuhn. Please look into this. If you understand, it will be easier for you if this is asked in the exam. Any question on Cohen-Kuhn? Remember, sometimes the input is not 1. Be careful with the input. Okay, in this case, is 1. But sometimes not 1, then K has to be divided by that input. The steady state value has to be divided by the input. Any question?